Okay, well, welcome everyone to the first Corundum developer meeting of 2023. Hopefully this year brings, some good stuff. Hopefully it's better than 2022. All right, so let me go ahead and get started with this here. So mainly we just have some status updates for today. Let's see, I went ahead and cleared out a couple of things, but there's not a whole lot new. I didn't get a whole lot done over the break. Mainly, I did some more work on the AXI virtual FIFO, and that's looking pretty good at this point. And then I also had a discussion with Leon on Zulip about CRC computation, and that got me thinking about how the CRC is implemented in the Mac modules. And I realized there was a pretty significant optimization that I could make. So I did that and saved quite a few LUTs. So more details on that over the next couple of slides here. All right, so first up though is the FIFO memory inference bug that we've discussed briefly at the past few meetings. I know the current status on this is that it was reported to Intel. I don't know if we have any news on this. Oh, Joachim just joined us. Ulrich, Joachim, do we know if there's any updates on this? Or is Intel still
I
working on
just
it?
looked at it today. There was no update. I
No
just
update.
pinged them and see what comes back next. Yeah.
All right, well, Intel is working on it, so fair enough. The ball's in their court. We'll circle back to this once we hear back, I suppose. All right, cool. Moving on. So, like I mentioned before, I kind of was triggered into thinking about some of the CRC implementations in the FIFO, or not in the FIFO, in the Mac modules, because Leon apparently has some need to do CRCs at a few hundred gigabits per second. He was asking about the implementation here and how scalable is it, whatnot. Actually managed to dig up a couple of interesting CRC implementations. It's on the Zulip if people want to take a look at it. One of them looks like, I think there's purported to run at a terabit per second or something like that, or a couple of terabits per second. It's a pretty wide interface. And all parameterized. Pretty cool setup. So anyway, I did some thinking about how things are implemented in the Mac module, and I realized that we could actually cut out quite a bit of logic on the receive side for the CRC verification and save quite a few logic resources. So the gist of it is that for the 10 gig, 25 gig max, the data path is 64 bits wide. So in every clock cycle, you get 8 bytes. But Ethernet frames are not required to be a multiple of 8 bytes in length. So at the end of the frame, you got to do something a little different to, deal with that difference, to deal with that partial cycle. So in the initial version of the Mac, I had CRC logic for 1, 2, 3, 4, 5, 6, 7, and 8 lanes. At some point, I realized that there's actually kind of an extra clock cycle bouncing around there, and I can remove 5, 6, and 7, and basically recycle 1, 2, and 3 by taking the output of 4 and looping it back around. And that saves some logic resources. And the way it checks to see if the FCS is valid is it computes the CRC of the entire frame, including the FCS, and then it compares the result against basically this magic constant. And if you get this magic number, then the FCS is good. Otherwise, there was some sort of a bit flip. But what I realized is that, well, if you roll some 0 padding bytes into this magic constant, you can actually just take the CRC all the way to the next 8-byte boundary. You just need to check for a different constant. And then you also need to make sure that everything following the frame is all zeros. So this actually ended up being a relatively simple modification where the frames, we have to add a little bit of code to basically force all the control characters after the frame to 0 from the standpoint of the CRC logic, and then compute a new set of constants, and then we can remove all of this partial CRC computation logic, and we only need the logic for all 8 lanes. And the result is that we went from 605 LUTs and 363 flip-flops to 255 LUTs and 308 flip-flops. That's a pretty significant savings. I mean, that's like 50% right there in LUTs, more than that. And flip-flops, we also saved a fair number. So Ulrich and Joachim, you might as well try this change out on your Stratix devices and see if it saves you much logic resources, because I know you guys are running out of room on that thing. So saving a couple hundred LUTs here is times however many ports is definitely going to be helpful, I think. So the next thing that that's on the back burner, I suppose, is take a look at the TX side, which is about 1400 LUTs, and that one has all 8 versions of the CRC logic. So potentially there's a way to do something similar where we compute it out to the full size and then basically back out some amount of zero padding bytes. But I need to modify the LFSR logic that I have to basically support rolling the state backwards. We'll see about that. There's potentially a couple of other options there. That's just a question of latency and whatnot in terms of making this work. But that's kind of the situation right now. We've got a pretty significant savings on the RX side. TX side, well, that's TBD. Yeah, so that's the Mac optimization that I implemented. This was just over the last couple of days. Let's see. Then there's priority flow control, which let's see. We talked about this before. I guess there's nobody on the nobody listening in right now that probably has anything new to add in terms of what needs to be done on the NIC side, on the software side, for priority flow control to work. But there's a PhD student in Spain, I believe, Antonio, who's starting to chip away at the PFC implementation and implementing some of the bits and pieces that are going to be necessary for this to work. So hopefully we'll have more details on this as things start coming together. All right, let's see. That brings me to the AXI virtual FIFO that I've been working on over the past few weeks here. And the idea here is to provide large packet buffering capability in DRAM and to store not only the packet data itself, but also sideband data, TID, TDEST, and TUser. To do this, what I'm going to do is split the encoding from the storage. So we have modules that will encode the framing and the sideband data, and then stripe that across multiple memory channels, basically. And the intent is to be able to support operation at 100 gigabits per second with all valid packet sizes and whatnot. And it seems like 2 DDR4 2400 channels will work, or 2 to 4 HBM ports. Main bottleneck is the memory bandwidth, so we need an efficient encoding scheme for that to work. So at this point, I have kind of the core portion of the FIFO working in hardware, and this is just doing the storing of data into the DRAM, and the encode and decode is the main thing that I'm working on. So let's see here. I did a bandwidth test with just the core portion of the FIFO on a couple of different FPGA boards, and the results are pretty promising. Went over this briefly last time, so I'll just go over it pretty quickly here. But we got around 49 gigabits per second for HBM2, which means 2 channels of HBM2 is not going to be enough for 100 gig Ethernet. And we got about 66.4 gigabits per second for DDR4 2400, which should be enough if you merge 2 of those channels together for 100 gigabit Ethernet. Let's see. So the current status of this, I've been working on the channel module, which is interfacing with one of the memory channels. And I did quite a bit of timing optimization for basically to get this thing to work properly with HBM, because it has to run at 450 megahertz for that. And I have a test design working with 16 of the 32 HBM channels active on the U50. I have not yet tried it with 32. I should do that just to see if it works. But yeah, it closes timing, and the bandwidth numbers look like what you would expect them to look like. So that's pretty good progress on that front so far. The next thing that I'm working on is the encoding. So I did some kind of back of the envelope calculations just to make sure that everything looks reasonable. And with the assumptions of 2 channels at 64 gigabits per second, which is a slightly conservative number from the DDR4 2400 number of whatever it was, 66 point something, and 100 gig Ethernet. So just the allowable frame lengths and IFGs and whatnot. Putting all this all into a spreadsheet, I was able to determine that seems like 20 bytes of overhead per packet should be doable when packing into 256-bit segments. So we take data coming in, 512 bits at a time off of AXI stream. We cut that in half into two 256-bit segments, and then we repack that across effectively a 1024-bit interface going out to the memory channels. And if we do that with 100 gig Ethernet, and assuming the memory bandwidth of each of those channels is 64 gigabits per second, so we have 128 total, then we can add up to 20 bytes of whatever per packet. And I think 2 bytes is probably all we need for framing, which leaves like 18 more bytes for TID, TDEST, and TUser. So that actually, you can put quite a bit of metadata in there. So that's a pretty promising number at this point. So yeah, it doesn't work at all with if you don't do the segments, right? With 512 bits, when you hit 65 byte payloads, you need too much memory bandwidth. So 256-bit segments with 20 bytes of metadata or whatever per packet, that's pretty reasonable. So over the next week or two, I'm going to hammer on this and hopefully get the encoding operational, and that'll polish off the virtual FIFO implementation. Let's see. So there's one other thing that I wanted to mention here. Well, not about the virtual FIFO. Let's see. Let's go over the rest of the status updates here, which I think are just all carryover stuff. So the idea with the virtual FIFO is that this is going to be kind of rolled into the DMA benchmark application, so we can also get basically a test of all the DRAM channels. Oh, one other thing I guess I didn't mention is that I did get the pattern generator and checker working in the kind of virtual FIFO test that I put together, which is the updated DMA benchmark. So we're not just implementing the control logic, we are actually implementing the whole data path, and we're checking the data that we're reading to make sure that there aren't a bunch of bit flips or something. So the DMA benchmark application is going to get this functionality eventually once I get it, dialed in and get the test benches updated with all of the hooks to support simulating the memory interfaces. So progress is being made on that front. It's not quite done yet, but yeah. And this is the application that I tested on the U50 with 16 out of 32 channels active. So things are looking pretty promising here. Right, the RAM integration. The FIFO stuff has been a really good test for this because I've discovered a few mistakes and a few shortcomings that I've made, that I've fixed. So that's looking pretty good at this point. Obviously, there's still a few other devices that it has to be implemented on. I don't have anything on the Intel devices yet, or 7 series devices, but we can circle back to that once I have the DMA benchmark application working with the DRAM interfaces and whatnot. And then it also has to be connected up to the DMA subsystem and the PCIe bar. So, one step at a time. Right. Let's see. So that's some more details on how the DRAM interface will be connected to the DMA subsystem and the PCI Express interface. So let's see. What else have I been doing? The batch completion write support. This has been backburnered for a while, but I did a bunch of work on this a while ago to get this operational. It needs some tweaking and some adjustments, and I also need to fix that PCI Express related issue in order for this to actually not cause the whole design to hang. But yeah, this will make its way upstream probably in a while. Let's see. So I got the graphs for that. Nothing new here. Right, and the variable length descriptor support, once we have the variable length or the completion write back support, then some of that code can be reused for the variable length descriptor support, which will open up more possibilities in terms of what can be done with packets, right? It'll be more efficient in terms of transferring the descriptors, and you can potentially include more information, more commands, things like that, which will open up possibilities in terms of various offloading things that are not really possible with the current setup. So that's to do. Hopefully going to get back to this soon. Right, so I got some more details on that. Let's see. Management softcore. This also needs to be done. I'm not sure if I have a specific timeline on this yet. There was some talk about possibly looking at doing some time synchronization, potentially White Rabbit style, in Corundum. So we'll probably have to get this operational for that. I was talking a little bit with Leon about the what was it? Oh, the JTAG setup. So the idea is that Xilinx has their XVC module, I think, and the idea is that that connects to the PCI Express hard IP core on the configuration extend interface, so you can basically poke at an internal JTAG chain through the PCI Express config space. So I'm hoping to get that integrated into Corundum such that you can take any of the Xilinx UltraScale boards and have a JTAG interface already available that goes into the application section, and then we can also redirect that for development purposes into the management softcore. So that's to do at this point. Another thing that I was working on a while ago that's at this point blocked on the softcore, and then there's also a few other changes that need to be made to the data path, is the 10G 25G switching, the ability to dynamically switch transceivers between running at 10 gigs and 25 gigs. So this works using some slightly hacked up user space code, but eventually the idea is that this will be integrated into the softcore, and we can just tell the softcore, hey, switch this thing to 10 gig, hey, switch this thing to 25 gig. But on a related note, one thing that I've been kind of mulling over here and there, it's like, okay, it's great that we can do 10 gig and 25 gig, but could we negotiate all the way down to 1 gig? And on the boards that support both 10 gig and 25 gig, there wasn't a solution that was immediately clear, right? If it only supports 10 gig and we have two QPLLs, we can set up one for 10 gig and one for 1 gig, and then we're good to go. The CPLLs, unfortunately, are not very flexible. They don't have very many possible divider settings and whatnot. So basically, if you don't have exactly the right reference frequency on the board, then you can't use the CPLL for 1 gig. So on all the boards that only support 10 gig, I think they have the correct frequency, but you have the QPLL available, so you don't need the CPLL. On the 25 gig boards, those are all running usually at the 161 megahertz reference oscillator frequency, and that doesn't work with CPLL to get 1.25 gig. So that kind of leaves you high and dry, right? You need 1 QPLL for 10, 1 QPLL for 25. How do you get 1 gig? So then I recently thought about, well, okay, what about oversampling? Could we just configure this thing to run at 10G, but then somehow run at 1 gigabit per second? So just last night I was thinking about this, and I did a little bit of back of the envelope calculation. If you take the ratio of the line rates, 10.3125 divided by 1.25, you get 8.25, which is actually quite a nice number, right? It's not like 8 point a bunch of junk, it's just 8.25. So what happens if you multiply that by 4 to get rid of that 0.25? Well, you get 33. Well, at 10 gig, you have a 66 to 64 gearbox feeding the transceiver. So 2 of these pack perfectly into the input of that gearbox, right? So if you think for gigabit Ethernet, that's 8p10b encoded. So if you take, say, your 1 gig MAC PCS PMA, that gives you a 10-bit output. You feed that through a 10 to 8 gearbox, then you replicate the bits across that 66-bit input into the async gearbox for 10G. It actually looks like this might work, at least for TX. The question then is, what about the RX CDR? I don't know if that would be able to properly track a 1.25 gigabits per second signal correctly when configured for 10G. I'm not sure if it actually has to track it perfectly though, because, if you do some, output tap selection and whatnot, to pick the correct outputs and look at where the transition is, even if you're off by, a bit with the CDR, you should still be able to get, low error output. So this might be worth an experiment for anybody that's, interested in screwing around with some of the transceivers, because this means that, that we can get all the way down to 1G. So food for thought, I suppose. I think that rounds out what I have in terms of status updates for today. So in terms of cutting a stable release, let's see, main thing at this point we need to do is get the FPGA or the software done, and then a few, I think, modifications to the internal data path, and then maybe the variable length descriptor support. We'll see. And then, yeah. So that about rounds it out for the status updates. I don't know if we have many questions or comments here. I know there's not too many people connected. Ulrich and Joachim, do you have any questions or comments?
Just about the interesting idea of oversampling for running 1 gig at 10 gig. I guess we could do the math, right? So the maximum run length is usually part of the data sheets of the transceivers. And that's actually the measurement for how many same values like ones or zeros all behind another are possible without making the CDR unlock. So I guess we could just figure out if even by datasheet that should work.
Right. Well, so my concern, so that's obviously one potential concern. The other thing that I was trying to figure out is that 8.25, that 0.25 means you're moving, a quarter of a UI, right? At a quarter of a 10G UI. So the the CDR is trying to track the edges. So if the edge suddenly moves by a quarter of a UI or half of a UI, then that could potentially trip up the CDR even on shorter time scales. So, but the flip side is that we're not looking at every single bit coming out of this thing, right? We're looking at every 8 or 9 bits. So even if the CDR does get off by a bit, that might not be an issue. So I'm thinking,
yes,
for this we might just need to test it and see what happens, right? Because you're not trying to get 0 errors at 10G, right? We're trying to get 0 errors at the divided, undersampled, whatever output. So I don't know, food for thought. It seems like maybe it could work.
Or maybe we can come up with another divider which actually fits the QPLL, but is a better suitable oversampling, like integer oversampling.
Right. Yeah, I guess it is possible if you wanted to screw around with the transceiver config to potentially run the QPLL still at the 10 gig line rate, but then implement some sort of a divider on top of that. I don't know.
Or I mean, even the other way
around. The whole idea is that, right? I mean,
go ahead.
Run the QPLL at a different line rate and then divide it to both.
Well, no. The other thing that came to my mind is, can we run the CPLL at a fraction of the QPLL?
Yeah, the problem with the CPLL is it looks like
limited.
The only potential input for that is coming off of whatever the external reference frequency is.
Oh, okay.
You can't feed it from the QPLL. If you could, that could potentially be useful, maybe. Like if you could run the CPLL off a divided QPLL, because you might be able to make that work. But at some point you very quickly start getting into limitations of the devices.
Yes. There are probably some ways how they support synchronous Ethernet or something, using the incoming clock on an unused transceiver that's locked to reference and use this to feed another one. No, that goes directly to the transceiver, bypassing any
Right.
PLLs.
So that is one thing I was thinking about. There is the TXPI, right? There's a phase interpolator in the transmit channel that you could play with. But that only helps you on the transmit side. That doesn't help you out on the receive side. And I'm not sure how far you can realistically push the line rate using that. That was one thing I was thinking about as well, is that you can set the transceiver. There is a divide setting from the QPLL. You can set it to a divide by 8, but then you still need to get rid of another couple of percent of frequency offset, which I think is beyond what the CDR can do. And I think it's also beyond what the TXPI can do as well. So yeah, I don't know.
And you say that the problem is only present on 25 gig enabled boards because they use the, let's say, the other side of reference clock from the PCS layer, like the 66B side.
Well,
okay.
No, it's only present on the 25 gig boards because you need both of the QPLLs for 10 gig and 25 gig, right? One QPLL for 10 gig, one QPLL for 25 gig, and then you have nothing extra. So I guess you could like dynamically reconfigure the QPLLs, but then you can only use 2 out of the 3, right? You could set one QPLL for 25 gig, one QPLL for 10 gig, and then you don't have 1 gig. Or you can do one QPLL for 25 gig, one for 1 gig, and you don't have 10 gig. So and then you got to reconfigure the QPLLs and
What about neighboring transceiver PLLs that are not connected outside?
Neighboring transceiver. Well, I don't think you can take a QPLL from one quad and drive another quad. You can share the reference clocks that drive the QPLL,
that's
but
right.
not the QPLL outputs.
Yeah, the output are not shareable. Yeah.
Yeah. Yeah, so I did quite a bit of thinking on this, and they actually have also, there's a way to feed the reference clock into, I guess, both the QPLLs and the CPLLs from the FPGA fabric. But all the documentation is like, this is for internal testing only. It's like, okay, so maybe it'll work,
they
maybe
really,
it wouldn't work. I don't know if that's
yeah, they really discourage to use this. Yeah, I think we should avoid this.
Yeah. So that's why I was thinking, okay, well, maybe oversampling could work. So I think it's, if somebody wants to do an experiment and just try setting this up and seeing if we can get low BER this way, basically take maybe 2 different FPGA boards, configure one of them for 1.25 gig, configure, and then just send PRBS data, configure the other one for 10.3125 and try oversampling, and we'll see if it works. I suspect on the transmit side, it'll work just fine. Because, this is all within, I mean, we're talking about, oversampling by 8.25. So being off by 1 here is being off by, 0.125 or something UI at 1 gig. So that should work fine. But it's just mainly a question of the RX direction and will the RX CDR work correctly? I don't think they've specified it to do this, but might just have to try it and see if it works. I don't know if you guys need to negotiate down to 1 gig potentially with your boards. But
well, it would be interesting, I guess. But yeah, but spending another 8B, 10B decoder encoder, I don't think you have enough room for it.
Well, yeah, I don't know. I mean, I don't think it would take that much additional logic resource. I mean, you'd have to have, your 1 gig Mac and your 1 gig PCS alongside this, which, yeah, it would take up a few more logic resources, but I think it's going to be a lot less than the 10G Mac and Phi, which are already there. So I don't know. Food for thought. And then I guess you're also on the Well, are we talking the Intel devices or the Xilinx devices? Because I know you're also using Intel devices, which are going to be slightly different in terms of the
Yeah,
clocking
this
configuration.
exactly. So we are with the 10G interfaces, we are on the Intel device. Our
Yeah.
1G device is a Sync Ultra Scale. So yeah, there
Yeah.
we
So for
can't
this,
negotiate upwards because it's a 1G base T5.
right. Yeah. Right. But I guess the question is on the Stratix devices, could you potentially do something like this? And if we're just doing oversampling, where you're not actually reconfiguring the transceiver itself, seems like it would. I mean, as long as the CDR works, then it might work. But I don't know.
Yeah.
I think it's
Yeah,
probably
actually,
operating
if we
far enough.
just run with,
Yeah,
go ahead.
I was going to say we're probably operating far enough outside of the spec that we're just going to have to test it. But what were you going to say?
Yeah, and the problem is that you just have like 2 instances and you don't know where the clocks are located on the maximum possible deviation you may have as per spec. So yeah, testing such thing is also not so well. There's not so a high probability, like proving this or disproving this. Well, it obviously disproves if it doesn't work, but if it works, it's not an actual proof.
Yeah, I guess
so
that's
I
true.
guess that's a little bit, yeah, that's the big problem with testing such things, right? So you actually would need to have 2 boards with highly configurable oscillators and move them from one edge to the other. Then I guess it would be fine. But I think for our use case, it would be just fine as it is, because we just use 10G and 1G, and we could just use multiple PLLs and then switch over from one PLL to the other. So I guess it would be fine for us.
Right. Yeah. Yeah, I suppose so. Well, like I said, just kind of food for thought. Could we do this if possible? It would be cool. Anyway, is there anything else that you guys want to discuss? Any other questions or comments or anything? I guess we don't have very many people on at the moment, so
Yeah, I will just start to implement some software to talk to the Stratix 10 SDM in order to, at some point, being able to do a firmware update via PCI Express.
right. Okay.
So I guess that's an open topic. We implemented an indirect register interface to the indirect register interface of the Stratix 10 mailbox IP. Yeah, I somehow didn't come up with a better solution. As on the one side, the location of this interface is really, really bad. That's in a position of the chip where we barely get into for
Oof.
routing restrictions. So
That's a
the
pain.
indirection helps with timing.
Right, because you can even potentially run that slower or something.
Yeah, and more register interfaces and whatnot. So it's working. So I could already interact with this interface, read out chip, what is it, device DNA, I think, or chip ID. No, Intel calls it chip ID. And I don't know,
idea.
firmware, JTAG ID. Yeah, right, same idea, and such stuff. So the interface seems to work. So next step is to get like voltage and temperature readings out of it. And then afterwards, hammering on firmware update itself. So like working from a 1-beat interaction to multi-beat to from read to write.
Right. Okay. Well, that sounds like pretty good progress. It's nice to be able to read out the JTAG ID, because with the Xilinx ones, I don't. Well, I guess you could do that using the ICAP or something. Anyway, yeah.
Yeah, so
Right,
that's
and I also posted an issue on GitHub, just starting to think about the firmware update format, what needs to go in there, what format that that needs to look like. So that
Oh,
might
okay.
be something to discuss at some point, is just what kind of stuff do we need to put in there. So
Yes.
let me see if I have that I can pull that up real quick and just see if there's anything worth mentioning. Yeah, okay. So it's issue 130. I can post a link to that.
Yep, great.
But yeah, so I have listed like some characteristics I think for a good firmware file format. Easy to generate, like it can be done with a shell script or similar. You don't need a binary program for doing that. Easy to parse, interpret, debug. So text is good for configuration and whatnot. Sufficiently extensible to support complex flash partition layouts and simple transformations. So I know on the Intel devices, there's some additional stuff that you need, multiple partitions plus like some sort of a little table indicating where things are, things like that. Also being able to support simple transformations is useful, like for Xilinx devices, swapping out the WB star address in the bit stream for fallback bit streams. That's a useful thing to do. So you don't need, two different bit files. Like you can just have one and then it just swaps out that address dynamically depending on what partition it's writing to. Having some mechanism for integrity checking, so hashes, checksums, signatures, something like that. And bonus if it can contain all the necessary information to also load the FPGA via JTAG. So with like a Xilinx bit file, you can do either without much difference. But for Intel devices, if you want to do that, would you need both the POF and the SOF, or can you load a POF via JTAG directly into the device? I don't know. Worth thinking about. So I think
guess you need
some sort of
bit swapping.
Yeah, I don't know. Well, bit swapping is potentially a simple transformation that would need to be done under certain circumstances. The current firmware update software also has some simple transformation capability. I mean, more in terms of hard coded. So when it's writing to parallel flash versus serial flash, it has to do bit swapping, and then QSPI versus dual QSPI, it has to what does that have to do? It has to basically split the nibbles apart and send all the upper nibbles to one and all the lower nibbles to the other. There's some repacking that has to take place. So supporting that sort of thing is not particularly difficult, I think. And then also maybe you want other stuff written into the flash as well. Like right now, I think we're just doing bit streams, but maybe at some point it would make sense to have like another block of data in there that could be read by the softcore, like softcore firmware or something like that, management firmware, that's separate from the actual FPGA configuration. Supporting writing arbitrary binary data as opposed to just an FPGA configuration is potentially useful. So yeah, I'm kind of thinking it's going to make sense to do like some sort of a compressed archive plus manifest file. So the manifest file can be text, and then the compressed archive, would just be a zip file sort of thing. Oh, I thought I stopped. Wow, Zoom is being screwy today. It says I'm still screen sharing. I'm not sure if I am or not. Hit stop sharing, nothing happens. Anyway, let me post a link to the GitHub issue here, so you guys can take a look at that. But yeah, that's worth thinking about in terms of what needs to be done for the Intel devices, since you guys are starting to look at the SDM and what the process is going to be. It would make sense to think about how are we going to put this together as a firmware update package that the firmware update program can read to do what needs to be done. Anyway, not sure if there's anything else that we need to discuss today. Joachim, did you have any questions or comments?
No, not really.
Okay, okay.
Yeah, just a status update. Perhaps as already mentioned last year, we are also now, looking at our performance and what we can do, what can be done easily, what's harder, what are the possibilities, where's the performance going? Yeah, these
Right.
answers have to be, these questions have to be answered now.
And this is mainly in terms of, I think you were doing some comparisons between UDP and TCP, and we're seeing some strange results, right?
Yeah, not only that, it's also regarding various packet sizes,
Okay.
payload sizes, small payload size versus, maximum payload sizes. And,
Right. I guess in some sense, that's like a question of packet rate. You know, how
right,
many packets
right.
per second can you
Mhm.
handle? Smaller packet sizes
Right.
means you got to handle a higher packet rate. So,
Yeah. So basically, what we are doing now is, or starting with, is, doing a first round of profiling to see, what's the context, what also the kernel might take up in terms of processing time. And always comparing that to a standard NIC, how it looks
right.
there, and then come up with possible solutions, hopefully. And
Actually, the one thing that I don't know if we mentioned before, maybe we have, the kernel has some packet generation capability.
right,
Packet gen kernel
yeah,
module. Have you guys played around with that at all?
yeah, we are using that.
Okay.
We have
All
been
right.
using that before when we have gave this page pool thing a first try last year.
Gotcha.
Yeah,
Okay.
works pretty good. You can
Right.
generate
that
all sorts of UDP traffic, multi-threaded, either kind of targeting one queue in MQNIC by having a constant port combination, for example, an address combination, but it can also do random ports, so you can basically make the RSS in the MQNIC do its work, and see interesting differences there. We already saw that just last year briefly, that, well, if you just hit one queue, well, then it's kind of CPU bound, of course. If you hit multiple queues in the MQNIC, then performance is obviously better. Yeah, but it's working great so far. No complaints. We have
Right.
been
So,
using that next to kind of a custom built packet generator, just using an Xilinx FPGA board and
oh, nice.
pumping out packets at line rate. But our generator is a little bit, limited.
Well, you have to put a lot of engineering time into that probably to get it to get the same feature set, you know.
Yeah. No, it's very simple. It basically can generate up to 20 streams, I guess, if I'm correct.
Oh, okay.
And we have included an earlier version of our scheduling thing, which makes it possible to assign bandwidth, outgoing bandwidth, to one of these streams.
That sounds like a pretty useful setup. Yeah. Yeah. So the only thing I was going to say about packet gen is that it seems like it could be a good tool for trying to separate the stack performance from the NIC performance, right?
Yeah,
Because
yeah, definitely. Yeah.
you're not going through the whole stack with the packet generation, at least on the transmit side. Receive side, I guess that's a slightly different story. So, and I guess it only works for UDP. If you're doing TCP, that's obviously handled differently because you have the round trip and the axe and whatnot. So
yeah, that's another story. Yeah. But to get a feeling and get see the differences between MQNIC and our special version, and on the other side the standard NIC, we'll start with looking at UDP packet processing, or packet processing on the lower layers, which is the same for all protocols. Of course, all the buffer allocation and hopefully then recycling, and that's what I wanted to kind of add as a last point. We're currently thinking about, or kind of defined it as a target, to get buffer recycling in, since that had a big impact when we looked at this last time. And
well, and I guess we don't just need to do that, but do that in a way that'll work on the older kernels, right?
Right. Yeah. That's the point. Yeah.
Right. It's one thing to toss in page pool. It's like that's pretty straightforward, but that's not as helpful to you guys because you're using a much older kernel that doesn't have page pool.
Yeah, there's another twist to that. We should not forget that. Last year, I gave it another try with page pool and the newer kernel, and for some reason I didn't investigate that further. The performance, the benefit was not really that great. So I'm a little bit wondering about whether, or most likely, the page pool implementation we have is perhaps not the whole story. We don't know yet. I mean, the patch is rather small. It's kind of adding 3 lines of code, and now I'm the suspicion is something is still missing to get the really good performance benefit out of it. Yeah, perhaps we'll also look at that. But as you said, on the other side, we have to concentrate on one of the older kernels.
Well, so what packet sizes are you guys using? Mainly 1500 MTU and smaller, or are you looking at jumbo frames?
No, 1500 and smaller. Jumbo frames is kind of not off the table, but currently it's the standard size. Yeah.
Right. Well, what I was going to say is that there's kind of another aspect of the page reuse, because you can cut the pages in half and then put 2 1500 byte frames on each page.
Yeah, sure. That's another story. Yeah,
which is kind of a whole nother direction to take that in. I mean, it only works if for MTU like 2K and less. I'm not sure exactly where you put the cutoff is, but 1500, you're fine. Somewhere 2K, you're not fine. Somewhere in the middle, you'll be okay. But
that also depends on our encapsulation, which we are doing.
Well, right, yeah, like I'm saying, it's dependent on overheads and whatnot. But yeah, 1500, you got quite a bit of buffer, so that's fine. But yeah, being able to put 2 packets per page, that cuts a lot of the overheads down quite a bit. So I know there are some NICs that work that way. I think the Intel NICs work that way. I don't think the Mellanox NICs work that way. But that's potentially something to consider doing as well, or at least worth some experiments.
Yeah, I mean, the kind of the takeaway point, at least for me, perhaps I misunderstood that or misread the code, is I'm under the impression that the Intel drivers, or at least the one we looked at back then, which was the IXGB driver, is exactly doing that in combination to achieve page recycling, or it's a necessary trick to get the locking of the pages, the reference counting of the pages right. And that makes sharing a page between two packets even necessary. At least that was my takeaway message. Perhaps I misread the code last year, but yeah, we are looking at this again now. So
Okay.
we'll have answers to that. We'll need answers to that.
Right. Yeah, I looked at the code a couple of times and I could kind of see what they were getting at, but I don't know all that much about the nitty-gritty of Linux kernel memory management and page reference counting and whatnot. So as soon as they were modifying page reference counts, I'm like, okay, this is beyond what I'm capable of figuring out. So yeah, I'll stick to the FPGA side of things. We'll have to find some Linux kernel memory management experts to take a look at that.
We'll keep you in the group updated. So
yeah, it would be cool if we can get that working and pulled into the upstream driver, because I think that would definitely help the performance. But yeah. I mean, I guess the other thing that a lot of these NICs do is various segmentation offloads, which definitely helps with the performance by reducing the packet rate. But I guess that doesn't help you with UDP. That'll only help with TCP.
Yeah, most likely. Yeah, well, we have to look at all these points and make sure that so the goal is to kind of attribute the needed time, the needed processing time to functions, to features, so that we can say, okay, these are the processing items and they take this much time in this scenario.
Right. All right. Well, would be nice to hear more as you guys start getting stuff figured out. So, yeah. All right. Is there anything else anybody wants to discuss? Or should we adjourn for today? Going once? Going twice? All right. I guess I will see you guys in 2 weeks. Let me see. What is that going to be? That'll be the 30th. Boy, already halfway through January.
Always a quick one on the beginning.
Yeah.
Good. See you in 2 weeks. Thanks.
All right. Sounds good. See ya.
Bye.
Thanks. Bye.